But I think what to go back both to the question about observables, but also like what's the point, right? That yesterday we talked about what can we learn about inflation from the CMB, and I actually showed you, right, although it was quick and at the end of the lecture, like I showed you that there are formulas that will probe inflation 50 e-folds before the end of inflation and actually tie it to predictions for what the primordial power spectrum are. What I want to say today is that the end of inflation, that this process of preheating or reheating provides an orthogonal sometimes, or at least complementary all the time, prediction from the inflationary model that can give us other observable consequences. And so the why is because there are a set of things that we can learn about the end of inflation that can help us to tie the physics from the end of inflation to the physics during inflation, and therefore actually give us a way to rule in or rule out whether or not the inflationary scenario is a valid epoch for the early universe. So the first thing, and this is something that's really deep in my heart because it's what I did as a PhD student 3 years ago, is to notice that this process is very violent. Now, I actually promised someone this morning I was going to point out that these field fluctuations, right, are nonlinear, and they end up having zero mean. Rho is a nonlinear function of the field fluctuations. These density fluctuations are huge at the time of reheating. Right? Maybe it's statistically isotropic, but delta rho over rho can become much larger than order 1. And it's modes, and they're all sloshing around together. Right? And so I end up with a universe that on the scales of reheating, which, by the way, for a gut scale model, I think the size of the co-moving size of the Hubble scale at reheating is like the size of an apple today. Okay, so it's right there, right? Nothing to do with Newton's apple or Einstein's. But anyway, so you can figure that the fluctuations that happened in the early universe now correspond to fluctuations that might have memory in, say, a gravitational wave background with wavelength comparable to the size of the apple that you hold in your hand. And so having those huge density contrasts and all of that anisotropic stress around, what we said was, well, then surely this should create a loud background of gravitational waves. And in fact, it almost always does. It actually probably saturates how loud a signal of gravitational waves from cosmology could possibly be. Because so much of the pressure in the stress energy tensor contributes to the anisotropic stress that it basically gives as much gravitational waves as is allowed by the dynamics of the system. Now, this is an old plot, but it's actually one that's totally consistent with our expectations of these predictions today. So in the purple and the blue sort of mountain bumps, right, are what the gravitational wave signals from this vanilla preheating might look like if it happened at 10 to the 15 GeV or at 10 to the 9 GeV. Right? So no matter what the energy scale of inflation, the gravitational wave background is still really, really big if I measure it in omega GWH squared. What happens is the location of that peak shifts as the scale of inflation changes, right? Because as the scale of inflation changes, the size of the Hubble scale at the time of the process changes, and therefore it changes the frequency of the gravitational waves that we see. And so if inflation were at such a low scale that the Hubble scale at the time of the transition isn't like an apple and is more like a LIGO, right? That's a unit of measure, right? Maya? Anyway, then this peak, right, would intersect with, say, some advanced version of LIGO. And why that's exciting is because the traditional primordial power spectrum, if you remember from yesterday, right, is dependent on the energy scale of inflation. So a lower scale inflation would make the inflationary gravitational waves unobservable, but it would actually take the preheating gravitational waves and move them into, say, the LIGO band. This enhancement of gravitational wave, stochastic gravitational wave papers having to do, is basically having to do with the nanograv signal. I'm not going to say much about that other than it isn't in the nanograv signal. Okay. But in addition to actually directly determining the gravitational waves, these are so loud, right? I've saturated the amount of gravitational waves that could even be produced at that time, that the total integrated gravitational wave power might actually contribute to the number of relativistic degrees of freedom at the CMB, right? And now this is something that is I don't know, was surprising to us a few years ago when we really started to think about it, because that means that even if I don't know the energy scale of inflation, I might be able to see the imprint of the preheating signal on N effective. And maybe that would help me to understand if it happened or to rule it out if it didn't happen. Right? And so many of the models that we talk about intersect the limits from the total amount of gravitational wave energy that could have been around at the generation of the CMB. Another thing that could happen is primordial non-Gaussianity. So in this scenario, I have different regions of the universe. I have different apples that preheat with slightly different dynamics. As they interact with each other, that develops some 3-point correlation function in the CMB. I'm not going to talk about it because I don't understand it. But I think another extremely interesting thing, and I could, again, if I had all day, we might get to this, but it is absolutely one of my favorite things to talk about, is these huge overdense regions have a great potential for producing primordial black holes, right? Because I have large delta rho over rhos. Oftentimes those instability bands are right at the Hubble scale, which give conditions that could potentially be ripe for having primordial black hole generation. So other things that can happen. So if I take my potential and I modify it just a little bit, so I'm going from an m squared phi squared potential here to what's known as an axion monodromy potential. The potential looks, the functional form of this potential looks a little bit, well, much more complicated, but basically it's a quadratic that has a correction term that goes out a little bit, okay? The shape of this, the shape of the anharmonious, I made the word up before, but because now the oscillation of the field is not harmonic, the field dynamics itself have nonlinear terms, and I don't even need a second field in order to have the homogeneous mode of the inflaton decay into particles. This self-resonance, as it's called, because it's the field mode mixing with itself, can produce efficient preheating. But in the case where the potential opens up a little bit, so this is a little bit like having a minus lambda phi to the 4 term in my inflationary potential. What happens is in these potentials is that once I create this non-thermal spectrum of fluctuations, the restoring force due to the potential is a little weaker than Hooke's law. And I end up creating quasi-stable solitonic objects, which can clump, gravitate, move around the universe. These are what are called oscillons. And they just emerge from the dynamics of the simulation. These can be really cool to study, right? Because again, they're nonlinear physics that are a prediction of many of our favorite inflationary models. For people who got their PhD 3 years ago or so, you remember there was a time when the axion monodromy was the inflationary potential that we really cared about. And it turns out a specific prediction of that model is that the universe is dominated by these clumps of energy for which we have no understood decay process. That's it. I can also get much more violent. Okay, so m squared phi squared plus this chi phi chi is a violent thing. Axion monodromy is a violent thing, but I can do better. I can make it worse by honing in on the tachyonic instability and making sure that my model has a really strong, long-lasting, or as long as I can make it last, tachyonic instability. And that really comes from adding different kinds of fields, right? So I hope I've convinced you that these nonlinear processes are fairly common in a lot of inflationary models. So here's one that where I have a scalar inflaton or a pseudo-scalar inflaton, and it's coupled to a U1 gauge field. These are attractive because the gauge field dynamics can do interesting things with the inflaton, but they're also really attractive because if I have reheating, I've now reheated into a gauge field. And unlike the chi field where you might say, well, there are no singlet scalars in the standard model, there are gauge fields in the standard model, right? And so the existence of gauge fields and extensions of the standard model are pretty ubiquitous. And so I can either couple it using this W function, which some of you might recognize as sort of a dilatonic coupling or a kinetic coupling, where the phi field talks to the interacting field through its kinetic term, or I can add this chiral coupling, this last term, this FF dual. And I'm going to focus on the FF duals set just because I only have so much time. And I wanted to show some movies of what happens in one of these tachyonic instability models. But these are cool models because as the inflaton evolves, it's coupled directly to either the left-handed photons or the right-handed photons in this U1 gauge field. To understand that, I'm going to go through this really fast, but if I take my gauge field and I decompose it onto the two helicity states, so I literally decompose it onto right-handed and left-handed photons, I can write the equation of motion for those two polarizations of the gauge field, and I end up with something that looks like a wave equation, plus a term that has an unknown sign, right? So for different values of phi dot, the combination k squared plus or minus phi dot, that total thing can be negative, and therefore I can have modes that exhibit a tachyonic instability. Right? I said it was all about the effective mass. For certain values of k, I'm going to have a negative mass squared, and therefore I have tachyonic instabilities. And here's what happens. As the phi field is evolving and starts oscillating about its minimum, I see huge growth. First, I see it in, I was looking backwards, you see it in the blue curve, and then the red curve, and then the blue curve. As the field velocity changes sign, I end up creating right-handed helicity modes and left-handed helicity modes and right-handed helicity modes. And I end up creating all of these particles that exist sort of on the left-hand side where the tachyonic instability exists. This is a pretty low value of the coupling. But I can raise that value of the coupling, and I see that what really happens is that those instabilities become bigger and bigger and bigger, and I impart more and more and more energy into the gauge field. And so, as a parameter, parameterizing this by that coupling, once I get to a certain level, I actually can deposit all of the energy from the inflaton into these gauge fields within like a couple of oscillations of the field. Right? All of the energy is gone. Now it's in a U1 gauge field. There's nothing more radiation-like than a U1 gauge field. Right? And look what happens in real space. So I take the same simulation. Now I'm looking at one of the components of the gauge field. The box is approximately a Hubble scale, or it's on the Hubble scale. And as the simulation goes on, or as the preheating happens, I end up with these clumps, right? These really dense, these really localized regions where the energy density is really a lot bigger than the surrounding energy density. In fact, so much so that at scales near the Hubble scale, the density contrast becomes order 1. Right? Now, again, I could talk about primordial black holes for a week, right? But if you've done any work on primordial black holes, this is the test that you're first taught, right? Is that if delta rho over rho is bigger than 1, the size of the dimensionless power spectrum at the Hubble scale is bigger than 1, that's your indication that you have to worry about strong gravity. And that's the indication that you have to worry about the collapse into these primordial black holes. And that's something that we've been studying very closely, and I don't have time to talk to you about today. Additionally, and I'm just going to show this model, and then I'll move on to the fourth part of the talk. Models of what are called alpha attractors have become really popular. What's neat about alpha attractor models of inflation is that I have some inflationary potential, but I naturally, and don't ask me how, but when you do the string theory, you get an action that has a canonical term for one field and has a kinetically coupled term for the second field. And this looks a lot like gauge preheating, which you learned about 5 minutes ago, where I have my second field now has a modified kinetic term, and that modified kinetic term allows for a tachyonic instability. But what's really cool about these alpha attractor models is that if I look at the potential, there's a value, can I do it? There's a value of mu that parameterizes the potential at all times, including, say, 50 e-folds before the end of inflation. And that parameter mu, if measured by, say, the CMB, automatically tells me the parameters that define the dynamics of the preheating period. Right? So if these alpha attractor models, which up until now have been really consistent with the CMB, turn out to be valid models for inflation, then they naturally describe the dynamics of preheating and give us a way to make a prediction from those specific models. Oh, I had a thing that said that. Anyway, it happens. These are hugely violent, so violent that after the energy gets deposited through the nonlinear process, you have so much energy that it quickly cascades into modes that you can't trust, and my simulations crash. But that's okay. We learned something from that too. Okay. And they have lots of gravitational waves. All right, so before I end whatever section of the day this is, I do want to say that what my point of these lectures was to talk about more than inflation, we can get information about the end of inflation. But the information that we get out of the end of inflation can't be gotten purely by looking at perturbation theory. That we actually have to do the nonlinear dynamics of the system because all of our models of inflation, whether we like it or not, exhibit these instability bands, and therefore we have to treat them seriously when we want to talk about inflationary potentials as models of the early universe. And that can lead us then to making predictions that go to gravitational waves and effective constraints, et cetera, et cetera. And that this is particularly exciting for models of inflation that haven't been ruled out by the CMB, which is not something we get to see very often. Okay. I will, maybe before I switch over, I'll pause quickly for questions before I move to part 4. Yeah, maybe in the middle here.
The back reaction, what is back reacting with what there? Just like the inclined field itself?
Great. So the question was, what is back reacting, right? And I'm using the word a little bit cavalierly because sometimes when we say back reaction, we're really talking about gravitational back reaction, right? And we're talking about are there modifications to the expansion rate because of modes that are present. Interestingly, we just put out a paper on this a couple weeks ago, but that's not the back reaction that I'm talking about here. When I say back reaction here, what I mean is that the inflaton condensate, which is the homogeneous mode of the inflaton, that thing is driving the expansion of the universe during inflation and after inflation. But as I give energy to other modes, those modes react back on the inflaton condensate, causing it to break down. And that's the way I'm using back reaction here, is it reacts back onto the homogeneous mode of the inflaton. Great question. Yeah, Liz. Oh.
How are you measuring mu?
Oh, I don't know. I mean, they do it through slow roll parameters or something, right? So all the characteristics of the potential, right? That mu and m, right, define what the potential looks like way up on the end, where it is 50 e-folds before the end of inflation. And so I think m is easier to measure because you can just use the amplitude of scalar fluctuations. I think for mu, you might need other information. But if you can characterize what the potential looks like there, then you have a prediction for what mu looks like in the entire model, right? So it's a very top-down way of saying, here's my model, and then we can measure it one place and then make predictions of it somewhere else. You're just dying to learn lessons. Oh yeah, go ahead.
I have a question about the magnetic monopole problem and reheating.
Okay.
So are the magnetic monopoles created during reheating? And if so, then when are they diluted?
Oh, they were diluted during inflation, right? So they were created before inflation happened,
Okay.
and now they're just gone. So we never have to think about them again.
Okay.
Yeah, they play no role in our lives ever. Now, you can create topological defects during preheating or during reheating, because if you have a field that has a symmetric minimum, right, you can end up with cosmic strings or domain walls, and you can end up with other topological defects that occur in the fields after inflation, but generally not magnetic monopoles. Those were a gut scale thing that have now diluted totally away, and I never have to worry about them again.
Okay. Thank you.
Great question. Okay. I know we're waiting for lunch, so I want to keep everybody happy. I don't know how many jokes I have left, though. There's no more sound. I guess you're going to have to. All right, so I'm going to spend the last 19 minutes, and I want to be, the subtitle of this is what I wish I knew, right? And I really want to take a moment and like do a fireside chat and talk about the actual nitty gritty of doing these simulations, and maybe to some degree what they can do, but to give you some energy to go out and do them, but also to kind of understand the limitations of the numerical model and how to make sure that you can trust it. There's been, as I said, with the code that we've written, plus there's a code called Cosmolattice, plus a bunch of other codes that I'll put up in a slide, there really has been an explosion of people wanting to do these nonlinear simulations to learn about either reheating at the end of it or preheating at the end of inflation, the decay of modulus fields in the later universe, early dark energy fields that might have decayed via some nonlinear process, et cetera, et cetera, et cetera. So lots of places where it's clear that nonlinear physics is important, and we need a numerical simulation in order to do that nonlinear physics. And I think that we've all produced, if I may say so, some pretty beautiful codes that for the most part are pretty user-friendly, that allow you to put in the physics that you're interested in and to get out an answer. And so I'm not here to say, use my code, use Danny's. I'm not here to do that kind of advertisement. But I am here to give general lessons that are always going to be important when doing lattice simulations. When doing nonlinear physics in these scenarios, what are the things that will make sure that your paper doesn't get rejected by the referee, which for some reason is always me, when it comes to making sure that you can trust your numerical system. And within that, I want to say that as far as culture goes, people who do numerics tend to be really, really friendly. Because we spend a lot of time by ourselves at our computers. And so when anybody emails us, we're like, human, nice to talk to you, right? And so really, if you have a question, like reach out, right? We're not going to be like, I need to be on your paper. We're going to actually give you the answer so that the community can learn a little bit something about what the numerical system looks like. So again, simulated preheating goes back a long way. And it probably, I think the first there were always little codes that people wrote to do nonlinear physics in small lattices. But the field really exploded in the year 2000 when Gary Felder wrote LatticeEasy, which was the first sort of distributed lattice program that anybody could download and use to study the dynamics on the lattice. And so a lot of the codes that we see today, including mine, which is up here somewhere, are built with many of the same tools and decisions that were made when Gary Felder wrote LatticeEasy back in 2000. You'll also note that many of these codes were sort of written in the 2007 to 2012 period. That was a really interesting time in computer history. That was when Moore's law still meant that you could buy a bigger computer next year, and it would be substantially more powerful than the computer you bought last year. And so there was a huge development of tools over that period of time because problems that LatticeEasy couldn't deal with because of its very structural nature could be seen by other types of doing problems because of the increased capacity of the computers around us. And you can also see from these dates that basically nobody has written a code in the last 12 years because computers really haven't changed very much since then. And I'm also missing some citations here just because they're, in addition to the codes that were written to do cosmology, there are codes that weren't written to do cosmology but can be applied to cosmological contexts. So here's the big point, right? So when you sit down and you start to look at a numerical product, what you do is you take equations that you say derived from an action, a set of beautiful coupled partial differential equations, and you say, I'm going to take these partial differential equations and I'm going to define them now at a set of points. And I'm going to take those points now as a proxy for the field that I started with. Now, it may not be surprising to you, although it is surprising to you, that when I make this choice to discretize space, I'm doing more than evolving a continuous field at discrete points in space. I'm actually taking my continuous problem, which is the problem of hitting Jell-O with a hammer, and redefining it as a discrete problem. Right? So I have, when I discretize space and time, I really am changing the nature of the problem itself from a continuous problem to a discrete problem. Okay, now, again, why shouldn't you be surprised by this? Because you've all taken quantum mechanics, right? And you know that quantizing things changes the system. And that there is a limit. There are things that I can do to connect a quantized or a discrete system to a continuous system, but those things are only, but I have to be careful about what things I compare from the discrete system to the continuous system. So there's nothing wrong with my discrete system. But if you're going to do numerics, the first thing you have to realize, you have to say to yourself is, I'm making a choice not to simulate the continuous system. I'm going to simulate this discrete system. And so the prototypical example of that is, of course, the wave equation, right? So I take the plain old wave equation. This seems so simple given the things we were talking about 5 minutes ago, right? Of course, to put it on to do numerical solver, I have to break a second order differential equation into a coupled set of first order differential equations. But then when I discretize that, that's not the way you pronounce that, when I make that discrete, what I end up doing is I replace the Laplacian with what are called stencils that compare the value of fields at different points. Okay, so I've gone from the Laplacian, which now this is that thing when calculus comes back to bite us, right? Because in calculus we were taught that all the derivatives are the limits as h goes to 0 of something, and then the mathematicians tried to convince us that that really meant something at a point, right? Now we're sort of kicked in the butt by that because it really is now the Laplacian as I calculate on the lattice is not something that's defined at a point. It's a function of nearby points. Okay? And so the nature of calculating the Laplacian on the lattice is not the nature of doing a derivative, but doing a comparison of a bunch of different parameters, or doing a comparison of a bunch of different things. And therefore, my discrete system is not actually a set of partial differential equations, right? It's actually a set of coupled ordinary differential equations. Okay? And if I write it in 1D, the Laplacian just reduces to this expression where delta x is the spacing between things. Now, I've given this talk only a couple of times, but no one's gotten the question right. I shouldn't set it up like that. Have you seen this before? Who's seen this before? This exact equation. You have. Oh, where have you seen it? Just shout it if you know it. Okay. Again, before that, where did you see it before that? Oh, before that. You guys are thinking about the same thing where I take a problem and I discretize it. You actually saw this before that. Before that, well, I don't know. After that. Remember the blocks and springs? Yeah. Right? Math methods, maybe? Second semester, second year oscillations and waves. All right. This is the equation of motion for the blocks and springs. Right? It is not the equation of motion for the continuous system, right? You did the blocks and springs, and then you let delta x go to 0, and you did the calculus again. You calculatized the system. Now we're uncalculatizing the system, right? Because this is the exact system for a set of finite blocks and a finite number of springs. And we usually write that, so let me go back to, 1 minus 2, 1, the pattern that appears as I go from one point to the next, right, is given by this matrix operator 1 minus 2, 1. And you remember from that math methods class that you took this operator and you said, well, for each of the modes of this system, I'm going to have eigenvalues of this operator which correspond to the frequencies of those modes. And then I'm going to have the modes themselves, which are the eigenvectors of this system. And so if I do that same thing now and I calculate, well, what is the dispersion relation, right? So I take the eigenvectors and I calculate the wavelengths. I take the eigenvalues and I calculate the frequencies. What I find is the most important thing that I'm going to say to you in this 20-minute block. And that is that the system does not have the same dispersion relation as the continuum system. This is not a deficit in the way that we're doing the analysis. It's actually going to turn out to be a benefit. But this is what we mean when we say the physical system is different. Even if you did perfect, noiseless simulations of a beautiful discrete lattice, you are not simulating the continuum system because they don't have the same dispersion relation, right? A mode with that frequency in your numerical system is not going to have the same frequency in your continuum system. But I do notice that if I do numerical tricks like add more points, then down here, down here, right, more of the modes line up with the modes from the continuum system. Okay. This leads me to something that I always say, but nobody ever believes me, right, until they do it, right? But when I create a lattice to do my numerical work on, there are some modes that I call the modes I can trust. The modes whose evolution, because of the nature of their dispersion relation, mimic the physical system well enough to say that really reproduces the physics at those scales. The high frequency modes, which, depending on how you measure it, could be most of the modes, are only there to ensure that you can trust the low frequency physics. Okay? No, I did a better time integrator. No, I got rid of all of my energy dissipation. No amount of any of those arguments will get rid of the fact that if you want to say, I'm reproducing the physics of the continuum, you have to have junk modes. You have to have high frequency modes around to ensure that the modes that you care about are resolved correctly. Now, we can play little tricks, right? So what was a 3-point Laplacian, you can turn to a 5-point Laplacian, right? So maybe some of your supervisors have told you this, like take a better derivative. And what I find is that those sort of tricks do help, right? Like the red curve moves up to the blue curve, and maybe there are a couple of modes here that I can trust, right? That I can trust with the 5-point stencil that I couldn't trust with the 3-point stencil. But it doesn't really help, right? Like this is a trick to give me a couple more modes, but it's not going to give me all of the modes. And it surely is not going to allow me to resolve the physics anywhere near what I think the limit of the resolution of my system is. Okay. So you have to look where you can trust. Okay. I have 5 minutes. I have plenty of time. What do I mean by where you can trust? Everybody wants a prescription, right? Like, is it the first half of the modes? Is it the first half of the modes in log space? So the answer to this is actually, I'm going to tell you about it. Let me tell you about Gabe. Okay, I'll get back. Think about that while I tell you about Gabe. So I do have my own software. Again, I'm not selling it, but if you want to use it, go ahead and use it. Just cite us, right? I'm happy to answer questions about it. It's easier for me to answer questions about Gabe than about other software, but I'd even try to answer those questions for you if I could. It takes space, it chops it up into a lattice. It's named after our dog, may he rest in peace, as most backronyms are, what it actually stands for. It's not particularly important. So you take a physical system, and if you wanted to put it into a problem like Gabe, you have to, as we did yesterday, actually define the parameters of the system. I'll put these slides up because I'm going to go through them sort of fast here. You'll note that the B that I talked about when I rescaled the clock yesterday now appears as the B where I rescale space and time in this code. That's not a coincidence, right? Because I wrote both of them. Which through the Friedman equation actually fully defines how I can do my dimensionless variables, because B is going to be the scale of the physics of the field, right? That's what sets the clock of the field. The Planck mass sets the scale of gravity. And so those two scales come together to tell me what the units of the problem have to be. You could choose B, but you can't choose the Planck mass because you can't choose what gravity is. So in general, in my code and in most codes, the fields get redefined by the Planck mass. And therefore, field derivatives and things have things like the Planck mass times B. Again, I think I can go through this kind of, I want to make sure you know that this is important, but I'll post them. And therefore, for any potential that you have, the art, or the first bit of the art, is to choose the rescalings that give you the resolution that you want, or put it in the dimensions of the problem. Okay. The only get one. This refers to the fact that if I'm able to rescale space and time to adjust to a clock, I can't rescale space and time to adjust to more than one clock. Right? So if I have, this goes back to why did I set m chi equal to 0, right? If m chi is much less than 0, I can't set my numerical system to resolve properly both the oscillations of the phi field and the oscillations of the chi field. One of those has to be a ratio that shows up in the code. Blah, blah, blah. Maybe I'll go back to. So when I was saying, what do you have to trust, right? So here's the answer to that deep question. If I'm going to set up one of these numerical simulations, I don't know before I do the simulation the extent to which I can actually trust the modes, right? I know that adding more points, adding a higher resolution, will allow me to trust more modes. But I don't actually know if I can trust the system until I run the system. That makes sense? Like, I don't know if I have enough modes until I find out if I have enough modes. Meaning, I have to continuously change the numerical parameters of the code to make sure that the physics that I'm interested in doesn't change. This is what's called a convergence test. And if you write a paper using these lattice codes and do not talk about your convergence tests, then you will not have it accepted. Right? Because this is the key to making sure that I have all of the physics that I want in a place in the code, in a place in the simulation, that I can really trust. So I add more modes. Does the answer change? I make the box bigger. Does the answer change? I make the box smaller. Does the answer change? I change the time step. Does the answer change? Once I've converged to the answer, then I have confidence that the modes that I'm talking about are trusted, that I can put them, they're in the regime of validity of the numerical simulation that I have. I don't care what your conservation of energy is. I don't care how well you're approaching the system from the standpoint of how well are you evolving the discrete system. Because what we want out of the simulation is the information about the continuum system, which means that I have to show that the results of my simulation are independent of my numerical choices. So let me give you a quick example, and then I'll stop. So going back to vanilla preheating, I have these variances that just help me to understand the stages of preheating. So at the beginning, I have two fields that are in the Bunch-Davies vacuum. They're slightly different because one of the fields is massive and one of the fields is massless. When parametric resonance starts, in the chi field, I see bumps at certain values of k. This I trust, right? This is what we expected to happen when we talked about nonlinear processes. There are certain values of k that are special, and there are certain values of k that get excited. Nothing's happening in phi yet because, and I apologize for the bad word again, back reaction hasn't started happening. At some point, back reaction starts happening. I get scattering with the fields with each other, and eventually I end up with these somewhat smooth distributions, which may or may not be thermal or may not lead to thermal, but they look a heck of a lot more thermal than the distribution with just a couple of bumps in it. So I do this simulation, and I want to ask myself, is this a spectrum that I can trust? Is this actually the answer that happens when in the continuum system? Because I'm starting to see that there's power in these modes that go beyond halfway through the box. So what do I do? A convergence. Oh. What do I do is I do a convergence test, which I thought I had on here. Imagine I show you a slide now with 2 different resolutions that show the same thing. Okay? But I do a convergence test where I show that the parts of the spectrum that I'm interested in are independent of the number of points that I have. I double the resolution, I get exactly the same spectrum out. I'm really happy. I have a simulation that I can trust. Preheating happened. However, let's say I go on to say, well, does this produce gravitational waves? Well, the equation of motion for gravitational waves are sourced by the traceless transverse part of the anisotropic stress tensor. I can solve this equation alongside the fields to calculate what the gravitational wave power spectrum looks like from this process. And so here's what it looks like. So at the beginning, nothing. Then some bumps. Then a hump. Then some crap. Okay? So I have what looks like here is a primary feature that corresponded to the scales of the problem that I cared about, and a secondary feature, which is way over on the right in K-space, and would be pretty impressive if it were real. How do I find out that it's real? I do a convergence test. And what I find is, on the left-hand side is at some earlier time. On the right-hand side is the final time. And I can see that that second peak depends on the numerical parameters of the system. And why this is so important is because the convergence test that I'm doing depends on the physical thing that I want to talk about. A simulation that passes a convergence test for one thing that you want to measure might not be a system good enough to measure something else, because the gravitational wave power spectrum has these higher derivative terms and is therefore those modes reproduce the continuum less well than the Klein-Gordon equation reproduced the continuum. Okay? And so what I'm saying is that that feature, which is clearly resolution dependent on the right-hand side, isn't physics, right? It's numerics. But you can see how, if you didn't listen to me right now, you might have said, holy gosh, that's a really big peak. In fact, you might have written a paper that shows this really big peak and how LIGO is going to see gravitational waves from just about anything. And then you do a convergence test, right? And you find out that it's wrong. Okay. Now, I'm a little bit like, this is one of the things I'm most mad about, because this is a picture from my thesis which shows this numerical instability, which people, anyway. I don't have a few extra minutes, but I don't have a few extra minutes. There's this great example, though. So if you're studying oscillons, right, I mentioned that these objects stay around and we have to watch them decay, something Islam and I have talked about a lot recently. It turns out that they don't. And the reason that they don't is because they quickly go to the part of the simulation that I can't trust. And that's another talk. And so I will end with, I'll leave this up as we break for lunch. But I did ask my students, like, what are the, if you were talking to a bunch of graduate students, a sizable fraction of which will want to do simulations like this someday, what advice would they give you? If you've done any numerical work, you will not find the top one surprising. Just do it. Like, do it yourself and use print statements to find out why things aren't working. Write things down, plot it out. These are the strategies that help you to understand where your code is going wrong. But I want you to remember that doing numerical simulations can be a hugely rewarding tool and perhaps the only tool to study nonlinear physics, you just can't trust them unless you do a convergence test. And then I'll end there. And I don't think we have time for questions, but we have time for lunch. So are there any urgent questions? I shouldn't say that. Go have lunch. Be back at 2. Yeah.
Discussing